Sorry, what do you want me to do?
No, sorry. There's not display about this. Can you go back to your presentation? Let me guide you here. Go back to your presentation, PPT. Full screen mode, please.
Okay.
Yeah. Let me assist here. Yeah. Click on display setting, the title.
Oh, yeah.
Display setting, duplicate slideshow.
Is it fine now?
Yeah. Yes, sir. We can start with the presentation.
Sure. Super. Thanks. Okay, so thanks. This is Kamal. I'm from Infosys. I'll spend the next 10 minutes in talking about our innovative methodology, narrow transformers in Gen AI space. I've got 6 items to cover in 5 slides. I'll quickly switch on to the slide 1. So the problem statement. I hope you can see the screen. Yeah. So the problem statement, right? So we know that Gen AI has been augmenting variety of tasks, right? All text tasks, code tasks, and multimodal tasks, right? Let's take code tasks for example. At Infosys or any enterprise for that matter, if I want to adopt large language model to augment a code task, either it is code completion, generation, validation, or documentation, I have to choose a large language model. And there are variety of family of large language models. You have Code Llama, Code Gen, Star Coder, and so on. For this discussion, let's consider Star Coder base, which was built with Hugging Face support, right? With community support and Hugging Face support. Now, at any point of time, I have an option to choose between 2 models, a smaller model and a large model. Let's say Star Coder base 1.1 billion and a Star Coder base 3 billion. Now my point is, at any point of time, I would prefer a small model over a larger model, because a small model, obviously 1.1 billion into 4 bytes will become your 4 GB, 4 to 5 GB, as opposed to a 3 billion model, which would demand 12 GB to 13 GB space, right? So I would anytime choose Star Coder base 1.1 billion over 3 billion, because it will occupy less RAM, it demands less compute, and so it is cheaper to inference a 1 billion model over a 3 billion model. Even if I have to enrich further, if I have to fine tune, it will demand less compute to fine tune. But in reality, we know that a larger model is better than a smaller model when it comes to accuracy. So what I've displayed below is the big code models leaderboard. I've specifically picked 1 billion model and a 3 billion model. As you can see, I mean, Star Coder base supports 86 programming languages. As you can see, Star Coder base 3 billion has a better score than 1 billion across languages. The same thing holds good. The Star Coder base 7 billion will be better than 3 billion, 15 billion will be better than 7 billion, and so on. Here comes the problem statement. It will be better if we have a 1 billion model, which has its own advantage of demanding less compute time, effort, and cost, where it performs on par, as far as accuracy is concerned, on par with a 3 billion model. So that is the problem statement for this. The narrow transformer is going to address that. Right? Before I jump onto the solution, in enterprise, if I have to adopt a large language model for a coding task, in an enterprise project, at any point of time, a developer, he or she would need the code assistant for one specific programming language. At times for a MERN stack or a MEAN stack, majority of the times they need it for either a .NET or a Java or a Python. Even though your Star Coder base knows 86 languages, I would need code assistance for that period of time for one programming language only. Hence, the idea is to, can we enrich the Star Coder base to be efficient in one programming language? And when we do that, can it meet the accuracy of a 3 billion model? Before I jump on to what we have performed, I'll just tell you how industry deals these scenarios, right? Let's take Meta for example. Meta started from base. They spent like 82,000 hours of GPU. They used 1 trillion text tokens and built Llama. Now, Llama is good at text tasks. It is decently well at code tasks, because that 1 trillion also contains code, like it also contains about cricket and poetry. Then they further trained that Llama with, they removed that 1 trillion tokens of text they replaced with 0.5 trillion tokens of code. They further trained Llama and produced Code Llama. Now, this Code Llama is better at coding tasks than Llama. Then they further trained Code Llama by extracting only one language dataset from the Code Llama dataset, which is Python. They extracted only Python. They further trained Code Llama with Python. They did the experiment setup such that the Code Llama should improve its efficiency in Python and in other languages also. And there could be few languages which might get affected by it, but at least they made sure that there is no significant drop in the accuracy. Because eventually they want to improve accuracy across programming languages, even if they want to fine tune with Python dataset. And what we have done with narrow transformer is we picked star coder base. So star coder base was not trained on a natural language model. It was trained from scratch by Hugging Face and community for code. So we picked star coder base, which was trained by Hugging Face for 33,000 hours with code, and they released star coder base 1.1 billion model. We took the Java dataset from star coder base, training dataset. We further trained star coder base model, but the difference is our experiment setup is novel because anyway, our experiment setup is such that we wanted to focus on improving the accuracy of that one specific programming language only, Java, without worrying about the rest of the programming languages. And so our experiment setup eventually built NT Java 1.1, which just demanded 0.02 trillion tokens, and we trained only for 1,440 GPU hours. And as you can see it in the table, the NT Java 1.1, obviously it surpassed star coder base 1.1. It also surpassed the accuracy of star coder base 3 billion model. So 3 billion model scores 19.25 and we scored 20.2. Now, why this is novel is even the Code Llama study, or there are other similar studies like CodeGen Mono, which was built on top of CodeGen MeitY, Star Coder, which was built on top of Star Coder base. They were all done on a large language model on 15 billion and 7 billion released. So there was no research done on the models in the range of 1 billion parameter model also. So it is also novel from the point of view of the size of the language model, because that changes your setup completely, right? And this study on large language models was prohibitive for a lot of research organizations because that demands a lot of compute, 88,000, 33,000 and odd. But when you do a research on 1 billion model, you just need 1,000 odd hours of GPU to perform the research. Now, the next thing is even a quantized version of NT Java. So the NT Java, if it is a 2 billion, obviously it demands a 16-bit version demands 2 GB. A quantized version, 4-bit quantized version, which demands just 760 MB, surpasses even 1.1 billion parameter model. And so in Infosys, where we started offering this. So there's a video, I'll also show it from my desktop. We started offering this to all the trainees who join Infosys, right? There are 10,000 trainees who join at the same time. This is installed on all 10,000 trainees machine without any GPU overhead, because it runs, because it's 760 MB, it runs on developer desktop. Just to show how fast it is, right? So this is installed in my machine. It doesn't talk to a web API. It doesn't demand a GPU. So it processes in my machine and it gives code in my machine. So the same thing we have deployed for the 500 developers of financial services project and so on, right? So, and it guarantees data privacy also, right? But this is not just a benefit of NT Java. This is a benefit of any 4-bit quantized model. But I'm just using this opportunity to show the benefit. I'll switch back to the now how unique it is. Now this is not the only technique, correct? If you want to improve efficiency for one programming language, there are 4 different ways. One is probably you can train a model from scratch for one programming language. But as you all know, this effort has typically failed because you don't have such significant proportion of data set for one language, right? Only when you mix all languages, you have decent amount of data, because we are looking for terabytes of information. Point number 2, you can pre-train multilingual from scratch. As we saw, star coder base is good. Point number 3, you can just improve efficiency for one language by considering other language without a drop in other languages. 4 is narrow transformer, where without worrying about other languages, regardless of the performance in other languages. If you want to improve accuracy, this improves the performance of that specific language, which can even beat the performance of its predecessor. In the lack of time, right? See, we open source the models, code, and paper, assuming that there could be other research organizations who can build similar narrow transformers across programming languages, across model sizes, and all. And social impact and sustainability, if you have to summarize in a couple of lines, this demands less compute, and so it's better energy efficient. And language models are generally prone to be for CO2 emissions, the infra. This will reduce this CO2 emission. Thank you.
Thank you, sir. Let's start with the Q&A. Let me stop sharing the screen. Jurors, we open for questions. Any of the juror would like to go first? I would take Professor Nair first, since you were the last presentation. Professor Nair, would you like to go first?
Yeah, thank you.
Pleasure.
So you are actually extracting something from a bigger language model, right? A larger language model. That's what you said. And then retraining it. That's what I could understand.
Yeah, just only one. You're almost there. Only one thing is that we are extracting from the data set of the large language model, right? And then we are doing continual pre-training with the data set on that large language model. Yes, on a smaller language model. Yeah.
So when you say smaller language model, you have extracted the smaller language model from a bigger language, larger language model. Is it like that? Or you started from scratch?
Actually, what we did was the Hugging Face built the 1 billion model, correct, right? So, and they used data set, correct? So we took their data set on 1 billion model itself. We extracted only the Java, which was used to build 1 billion, and then further trained 1 billion with the Java, right? We are just eventually comparing with a large language model. So we are star coded base 1 billion uses a data set. Now we just extracted the Java from the data set. We further trained star coded base 1 billion with Java. That's all we did, Professor.
So your final model is naturally a smaller model.
Yes,
space, right? But when you make that smaller model, how is it that you extract something from a larger model?
Oh yeah,
that's what.
So there are two ways of extracting. So typically, right, people do synthetic data generation where they actually pass instructions to a model and then get data, right? But what we've done is we went to the source. You have the pre-training data set, correct? So from the pre-training data set, we just extracted the Java data set from there. So we are not extracting from the model per se. We are extracting from the pre-training data set of the model, which is Java, and then further training that model with the Java.
No, but when you say that the model which you have is a smaller model, then how did it become smaller is what I was wondering.
Oh yeah. So we didn't deal while only while comparing, we compared with the larger model. In the entire experiment, we didn't touch larger model. So there is a star coded base 1.1, which is small, and there is this training data. Now we just extracted Java from its training data, and we further trained the small model only. We didn't go to the larger model, right? We extracted the Java data set from the smaller model. We further trained the Java model from whatever state it is. We further trained for a few more checkpoints and then built NT-Java. Only while comparing, we compared with the larger model.
Okay, that's all from my side. Thank you.
Thank you, sir.
Yes. So just to again a follow up from the previous question. So when you say smaller model, it's not the case that there was a larger model and then you made it smaller. So it was a smaller model that you chose, and that model architecture, number of parameters, everything remained the same. On the other hand, if you compare it with a large language model for this kind of part, we can call that this is smaller.
Oh yeah.
Okay. And then you can do quantization and other things to make it a bit more smaller. Okay, all right. And then are there any specific tasks against which you have validated the performance of this specific model?
Oh yeah. So there are two kind of evaluation, right? One is the human eval, like the big code, what the big code follows, correct? So we did a human eval, and the scores that we presented is from the human eval evaluation. That's point number one. Right?
Task?
Sorry?
What is the task for which you use?
Code generation. Right. So the human eval does the code generation thing. So we did a code generation evaluated, correct? So that's point number one, and that's public thing. In fact, it is being evaluated by the big code as we speak, and it will come in the leaderboard sooner or later, correct? So that's one part. The second part is now for code translation, correct, right? From Java to other languages. So within an enterprise project, we deployed this for a code translation. And so it does all four: code documentation, code generation, code translation, and code documentation, correct, right? But for code translation, for some of the languages, it doesn't perform well because it knows only Java well, correct, right? So this cannot be applied for code translation kind of scenarios. But otherwise, for code completion, generation, and documentation, this is well suited.
Okay. Thank you. No further questions from me.
Thanks.
So while you're removing the original data, let's example in this case Java, now there could be a possibility that the data set you are using to further train it may be the subset or maybe not right amount of the data that can really severely impact and throw off the weight, and the model can really completely collapse. So what has been your experience while you're doing this kind of stuff?
Super, brilliant question. Because we started this project almost a year back. When we started, the only fear was like what you told, correct? Because all the research papers that we saw were all done on 15 billion parameter models, right?
Right.
And they are trained for one epoch, correct? Right?
That is a very wonderful approach you have followed. It's an innovative approach.
So we had this risk, right? Because we thought model will, in fact, will not even score as good as a 1 billion model. I thought it will even collapse further, correct? Now, as you said, right? Actually, now we trained for actually 1,20,000 steps is what we actually trained. It's almost 6 epochs compared to everything else. So, and another fear is that, just to add to the tension, right? Another fear is that probably it will overfit Java, but it's not like it's as good as a human being knowing Java as opposed to a human being knowing multiple languages and then knowing Java. The later is always better because you always use the nuances, structs, algorithms, and learnings from other languages also. So we also don't want it to learn, not forget the fundamentals of programming language at the cost of learning Java, correct? Which will decrease the score. So what we have observed is when we train till 1,20,000 steps, the learning rate plays an important role, because in other kind of setting, the learning rate is static. If it is 10 e power minus 4, 1 e power minus 4, it remains 1 e power minus 4 for entire one epoch or 1.5 epochs. But we have to gradually decrease from, after a lot of empirical tests, right? 1 e power minus 4 to 1 e power minus 6, the cosine decay, we have to do it from 0 till 1 lakh thing. When we do that, that times it doesn't really collapse, correct, right? And again, after 1,20,000, it started collapsing too. So 1,20,000 is a sweet spot, but that learning rate is the major learning in the entire thing. It took time for us to really figure that combination of learning rate, the start and the end and the cosine decay, correct? So that's the, but that helped it to retain what it learned, but still improve on.
What is the delta improvement you saw? Because finally decoding what happens in the weight is extremely difficult. You can't really go back and trace it.
Oh yeah,
What is
correct.
the final delta improvement in terms of really performance?
Okay. So as you can see in the big code benchmark number, right? So your for 1.1 billion model scored 14.2, 3 billion model scored 19.2.
Right.
This model scored 20.2. So it was starting from the 1.1 scored 14.2 for Java. 3 billion model scored 19.2. Our model scored, 1.1 model scored 20.2. So that is the growth we saw, Bhupesh.
But it's still not a significant improvement, because so much of hassle you're doing theoretical, it is good. But if you have a wrong data set, then it can really completely throw. And like a lot of Indian coders, what kind of data they really write, what kind of code they write. Okay, thank you. It's a good approach. But the final delta improvement is not very significant.
But just at one point, so actually for a 1 billion model, right, it surpassed accuracy of a 3 billion model.
Okay.
And what we are actually, this is a reference implementation, right? But what we are proposing is that a 1 billion model surpass accuracy of 3 billion model. The same thing you can apply it for a 7 billion model, and we expect it to surpass accuracy of a 30 billion model. So at any point of time, it will surpass the next billion model. That's our proof, right?
It's a good approach.
Thanks.
Good work.
Your question.
I just have one quick question. Have you considered something called knowledge distillation? So you learn from large language models by building a truly small language model rather than based on a 1 billion model, could be smaller than that. Have you tried something like that?
Oh yeah, actually, this research, right? In fact, before even we want to start this research, our idea was to use a knowledge distillation. So we started distilling, right, within our enterprise or one specific language, because again, the idea was to use a 1 billion model in place of 3 billion model. As you told, there are a lot of 350 million parameter model, which were like a Java adapted model, but their efficiency was better than the base 350 billion model, but it is still not better than like what the kind of numbers that we showed here. Hence, we were forced to try something like that. Now, this approach actually gave a better result than a knowledge distilled smaller model.
Okay, so in your open source code and in your paper, did you have a paper for this?
Yes, we have an archive page we published actually.
And you've reported the comparison between the knowledge distillation and your narrow transformer?
Oh, okay. So good point. So we compared between the larger and the smaller model. We didn't specifically report the numbers between a knowledge distilled and this number though, but that was done as an experiment before we started the project. Yeah.
Okay. All right. Thank you so much.
Thanks.
Thank you. Thank you, Jules, for your question, and Team Infosys, thank you for your time. We wish you the best with the education. Mr. Kamal,